Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Meeting Challenging Efficiency Standards with Bridgeless Totem-pole Power Factor Correction. The speaker is Alessandro Maggioni from our partner from Onsemi. But before we start, I would like to point out one thing. You will be muted during this presentation. This means that you cannot ask questions via microphone during the presentation. But nevertheless, you have the opportunity to ask questions during the presentations at any time via the chat function. And you can find the chat function in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are about 5 to 10 minutes in addition scheduled for this. And if we are unable to answer all of your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com. And we will, of course, try to answer all of your questions promptly. At the end of the presentation, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our events. You will also receive the link to the presentation in the next few days, and the recording of this session will be available at our website shortly. But now it's time to hand over to our speaker, Alessandro, and I wish you an exciting presentation.
So thanks, first of all, good afternoon. So thanks to Würth Elektronik teams for these opportunities and welcome to this session of Digital Days. My name is Alessandro Maggioni, and I'm responsible as Regional Marketing Manager for the EMEA region for the Advanced Solution Group inside Onsemi. In this presentation, we will try to highlight how to achieve, so with a Bridgeless totem-pole power factor corrector, the most challenging efficiency standard required by the market. So this is the agenda of today. So we will start with a small...
One remark, we actually cannot see your screen right now. Maybe you can try it again. Now, perfect.
Oh, okay, perfect.
Thanks.
So sorry for that. So here is the agenda of today. So we will start first with a small introduction of the AC/DC power supply market, where are used, how big it is, and the trends. So then we will talk about PFC, or power factor correction. So why is needed? So the solution can be implemented and the control techniques, especially in the CRM or critical conduction mode. High efficiency. Why there is a growing demand of energy efficiency solution. So a comparison between bridge and bridgeless totem-pole and which perform better. We will have a look on our solution for bridgeless totem-pole PFC controller. So our Onsemi NCP1680 based on a CRM control mode. We will also spend some slide introducing our evaluation board based on NCP6080, able to achieve up to 300 watt with very high efficiency. And then in the end, of course, sometimes available for any question and relative answers. So let's start. AC/DC power supply landscape. AC/DC power supply are extensively used in several vertical markets, including industrial, automotive, medical, smart cities, which is quite wide nomenclature, and cloud. More recently, the growing adoption of the wide bandgap devices, such gallium nitride, GaN, and silicon carbide, has directly impacted the expansion of AC/DC power supply market adapter. Over the past few years, owing the advancement in this technology, so GaN and SiC technologies have increasingly become more and more feasible also for commercial applications. AC/DC power supply are still the major power supply product type in the market, so accounting for more than 85% of the market revenue. So this was back in 2014, with the DC/DC converters accounting for the rest. This is driving the manufacturer. So as the demand of all of these products in the above market segment is increasing. So the production of AC/DC power supply is also rising. Back of these factors, so along with the focus on this revamping the electronic sectors, the global AC/DC power supply adapter market is expected to attain a market value of around $12.9 billion US. So this by the end of 2027. And is expected to grow at a compound annual growth rate of around 5%. In Europe, so the so-called Euro 5, so this means Germany, UK, France, Italy, and Spain, all the biggest share of the Euro power supply market. This is owing to the strong growth of industrial electronics, so industrial automotive sectors in these countries. PFC, so now let's look about why the solution and different control techniques. PFC, why? So there's a problem. Okay, so AC power has two components. So the real power of the active power, so also sometimes called average power, which is expressed in watt. And then you have the reactive power, so usually expressed in reactive volt amperes. As power is transferred along a transmission line, it does not consist purely of a real power that can do the work once transferred to the load, but rather consists of a combination of real and reactive power, so which is called apparent power. The power factor of an AC power system is defined as the ratio of the real power absorbed by the load to the apparent power flowing to the circuit. A power factor of less than 1 indicates the voltage and the current are not in phase. So this means reducing the average product of the two. And usually the current waveform does not follow the voltage wave. Here we have an example of waveform on SMPS without any PFC. So here you can see on top the voltage waveform, and here you can see the input current wave. Here, voltage and current are more or less in phase, so great. So this means that I will have a good power factor. Unfortunately, wrong. So measure here, the power factor is actually 0.6. So this results not only in power losses, but may also cause harmonics that travel down to the neutral line and disrupt other devices connected to the line. Here, you can see in the same condition, but adding a PFC stage, that current and voltage waveforms are very close each other. So with an improvement in the THD, reducing all of the others. How to move from left, so this is the without the PFC, from the right, which is the solution. So you need to shape, remember, you need to shape the input current in order to match the input voltage wave. So how? Insert a switch mode boost converter stage between rectifiers and the back storage cap. So now we have a simple example of why you want to have a very good power factor in your AC power line. So here you have 2 glasses of beer. So both are objectively full, and if you go to a pub or in a bar, so you will pay in both cases as a full glasses. But on the left side, you have a very poor power factor, so around 0.6, like here. While on the right side, you have a very good power factor, so well above 0.9. So I think everyone prefers to have the right one, or am I wrong? Control techniques. This is one of the control technique. There are several control techniques in the power factor correction. So CRM, or critical conduction mode, is one of the examples. And here is the with multiplier. So remember the goal. So the goal is to shape the input current to match the input voltage waveform. So critical conduction mode means that inductor current always goes to 0. Here on the left side, you can see a typical block diagram of a boost converter, so with internal reference multiplier. So the current shaping control varies the power switch as is described in here, so in the step 1 to 5. Basically, the internal reference multiplier here generated the reference voltage, so called VREF, so which is a scale version of the rectifier AC input shape, coming from the AC input pin through the resistor divider. When the power switch is on, so the current to the inductor ramp up until the voltage across the shunt resistor, so which is based here, is equal to the reference voltage. When the switch is off, the current to inductor ramps down until the current reaches 0. This is the result that the average current is then equal to the peak current in the inductor divided by 2 as a triangular waveform. So, long story short, so basically you're banging from inductor per current, sensed through the resistance shunt, to the inductor 0 current. This is one of many examples, so unfortunately we don't have enough time to cover everything in this presentation. High efficiency. Which is better, bridgeless versus bridge? So why there is this kind of demand? There's a high demand of energy efficiency solution. Over the past decades, environment concern across an array of industrial domain have forced the players in the global AC to DC power supply adapter market to lean toward the development of energy efficiency components. Most of the world's electrical energy is supplied to the AC/DC power supply. So as we saw in the first slide, so more than 85% of the total power supplies. And they are found in almost all mains powered equipments and devices. So this meaning that their efficiency has a huge impact on the operating cost, as well as contribute significantly to the emission. Here you can see the typical PFC circuitry, so a conventional boost. So the input bridge rectifier found in almost all the DC power suppliers contribute losses that present a challenge in achieving the highest possible efficiency figures. However, removing the traditional diode bridge, the PFC FET, and the boost diode in a favor of a bridgeless totem-pole PFC arrangement enhances the efficiency for the use of active switches. Most commonly, PFC use a boost converter to derive a DC level higher than the main voltage peak from a rectifier mains. So this DC level is typically 395 volt for a power supply designed for a universal input, so 90 to 260 volt AC. Is then regulated using an isolated DC conversion stage to produce the required DC output voltage for the PSU, so for the power supply unit. So, a valuable byproduct of this is that the line requiring the current follow the line voltage waveform, so giving, in theory at least, a unity power factor. The approach above is effective, and PFC can be designed to operate in several modes, so continuous, discontinuous, or critical conduction mode. So the acronym are CCM, DCM, and CRM, which are largely defined by whatever energy in the boosting inductor fully exhausted during each cycle or not. Normally, there is a 2% loss within the CDC stage and 1% in the line rectification and PFC stage. Although this is much closer to 2% during the operation at low line. With close to 4% losses at low line, there is a significant challenge in meeting, for example, the strictly 80 plus titanium standard level that requires to have up to 96% efficiency at 230 volt AC input at 50% load. So this is a specification which is commonly used, for example, in servers. Efficiency, bridgeless versus bridge. How to make a boost PFC more efficient? You always have to remember the golden rules. So better efficiency with fewer devices in the conduction path. On the right side, you have the typical PFC with bridge diodes. So you can see here in orange, you have the positive half cycles, so when which are the device are conducting, and in the dark gray, you have the negative half cycles. So here you have the input bridge, you have the boost FET and the boost diode. Both in the half cycle positive and the negative cycles, you always have 3 devices as conduction. On the left side, here you have the bridges totem-pole. So you can see it how it works. So the topology consists of 2 half bridge configuration. One half bridge commonly referred as a fast leg here on the right side, which switches at the PWM frequency. On the other, commonly referred as a slow leg switches at the line frequency. The fast leg switches perform the role of the switch and the diode in a classical boost PFC. So that is the switch's function to regulate the output voltage and shape into the input current to provide a high power factor and low harmonic distortion. The slow leg switches perform the role of the diode bridge in a classical boost PFC. So Active switches with low on resistance are utilized instead of diode, resulting in improved efficiency. The totem-pole PFC operates with only one slow leg and one fast leg devices in the conduction path, where the conventional boost PFC, as we discussed before, operates with two bridge diodes and one active switch or boost diode in the conduction path. So this means that fewer devices in the conduction path and active switches replacing Bridgeless diode allow totem-pole PFC topology to achieve the higher system efficiency and the power density than a classical boost PFC. Also, totem-pole PFC is a derivative of a standard boost PFC converters, where the bridge diodes are removed and therefore the boost circuitry directly interfaces with the AC input. So the key challenges with this approach are detection of the line polarity, current sense, and current limit implementation. Further, totem-pole PFC is a synchronous boost converter, so as opposed to the standard boost PFC implementation. So therefore, a zero current detection scheme needs to be implemented, as it is seen on our rectifier AC line. All the above mentioned requirements are of course implemented in NCP1680. It is also important to note the similarities to a standard boost PFC. For example, the criteria for selecting the boost inductor, the output capacitor, and the boost FET are exactly the same between the totem-pole PFC and the standard boost PFC. Now, let's have a look a little bit more in details about our NCP1680 Bridgeless totem-pole PFC controller. Here we have a table which is explaining the main topologies for power factor correction. Here we can go from a standard interleave booster, semi-bridgeless boost, interleave critical conduction mode to totem-pole, and the new Bridgeless totem-pole solution. So which are the advantages? First of all, the transistor. So for a CRM, you can choose whatever kind of FET you want, standard silicon, super junction FET, wide bandgap, so GaN or silicon carbide. While for the CCM mode, so means for high power, we strongly suggest to use only wide bandgap, GaN or silicon carbide. The switching frequency, so which is much higher. In CRM, we can achieve up to 500 kilohertz. Theoretically, up to 1 megahertz is possible as well. The advantage are, of course, an highest efficiency due to also to the low component count. In case of using again, you also have a zero QRR, so this means pumping up again a little bit higher in frequency. And then, we discussed before, also you can have the highest power density possible. The cost is more or less aligned with the other solution. Of course, considering that this cost can be also, let's say, various depend of which kind of power FET you are using. And then you can see the big jump in terms of efficiency, which is very close or even higher than 99%. Which other application you can use for, you can have for a Bridgeless totem-pole PFC? Basically, everyone. So everyone you need a PFC. Can be data centers, rack mount power supply, high power LED street lighting, industrial power supply, chargers, PSU, UPS, high power adapter, 5G telecom power supply, external power adapter. So basically, here you have to think that you can use it to match all the applications where, of course, a PFC is needed, and that efficiency and compactness are a critical parameter. So let's have a look a little bit more in detail of the device. So the NCP1680 is a critical conduction mode power factor correction controller IC, which is designed to drive the Bridgeless totem-pole PFC topology. Remember, so the Bridgeless totem-pole PFC consists of two totem-pole legs, a fast switching leg driven by the PWM switching frequency, and the second leg that operates at the AC line frequency. The topology eliminates the diode bridge present and the input of conventional PFC circuitry, so allow a significant improvement in efficiency and in power density. The NCP1680 is capable of a constant on-time CRM and valley synchronized frequency fallback. First of a new family with a proprietary current sensing architecture and proven control algorithms, the NCP1680 allows for a cost-effective solution without jeopardizing the performance. Which are the main features? First of all, we have industry-first mixed signal controller. This is based on a state machine core, so which is dedicated to totem-pole PFC topology. Easy to implement compared to existing totem-pole solution, cost-effective fast go-to-market, and you don't need too expensive software updates. It's based on a CRM architecture. So during the CRM, if the load is high, the switching frequency is low. But when the load reduces, the frequency increases. So this is because the inductor current is not going to the load. So this allows to optimize the performance across the whole load range. Frequency fallback is the first line of defense. So we reduce the switching frequency at light load, but when you still have the valley. So the second line of defense is the valley switching. So we actively detect valleys to check the safety. It's based on a proprietary current sensing. So we have proprietary sensing of the zero cross detection resistor. So we can also detect peak current value. We also use it for current limiting and protection, which is a more elegant solution. Traditional totem pole use a digital controller like MCU or a DSP, so which are necessitated of firmware and are more complex. So they are also controlling the switch timing using a Hall effect sensor. So our solution replaces this Hall effect. So this means that the control loop is internally compensated, and this means that also the external component can be, some external component can be removed. Of course, it also comes with the main safety feature required, like brownout detection, power factor OK indicator, sort of power good for the cascade application, soft and fast overvoltage protection, bulk under voltage protection, so internal shutdown, and a cycle-by-cycle current. Which are the market and application? Basically, it can go in all the application where a PFC with high density and high efficiency, up to 350 watt maximum is needed. But here's the limit of the CRM topology, not of the device. And then is housed in an industrial-friendly SOI 16 leads. Which are the totem pole scenario today, and which are the advantage from us? So again, as we discussed, so existing solutions on the market are based on complex MCU-based solution. So customer needs to write software code, costly current sensing method, and to implement this topology. 6080 is the industry first mixed signal controller, state machine core, so which is dedicated, fully dedicated to totem pole PFC topologies. So now you have to choose your path wisely. So today, if you want to look at totem pole PFC solution, you have only two choices. Or you can go with mixed signal, and this means to move to Onsemi NCP1680, which is based on a simple sense resistor or current sense. Or you can move to the rest of the market. So, and this, you have to work on the full ecosystem. So mixed complex solutions based on all effects, software development kits, firmware, and so on. So on the other side, NCP60 is simple, integrated, coding-free, and excellent light load efficiency and standby power. Moreover, we just received a couple of weeks ago the Electronics Design 2021 Power Best Award. Now, let's have a look about a few slides about the demo board based on NCP6080, so 300 watt demo. The demo is, as we discussed, is up to 300 watt, and it is done utilizing 15 million GaN FET. So the evaluation board, motherboard, and the daughter cards are shown here. So you can see the daughter cards put in vertical, and here's the motherboard. So here you can see the main spec. So input voltage range, which is universal from 90 to 165 volt AC. The line frequency range is 47 to 63 Hertz. So the output voltage is the standard PFC voltage, so 395 volt. And the output power is up to 300 watt. And then also you can see here all the components provided by our friends Würth Elektronik, like inductor differential, the PFC inductor, the common mode choke, and the backup. As shown in the picture here, the slow leg switches are high voltage silicon-based FET, so also known as the super junction FET. And the fast leg switches on the daughter board here are enhancement mode gallium nitride, so GaN devices. Since the NCP6080 employs a CRM control architecture where the inductor current is set back to zero before the next switching cycle, low reverse recovery charge QRR of super junction FET can also be utilized for fast leg, albeit with slightly inferior performances, but better cost structure. As a controller, the NCP60 is completely agnostic to the fast leg switches technology, but wide bandgap devices such silicon carbide or GaN are strongly recommended for optimal performance. SiC is a good choice for lower frequency application, while GaN is an excellent choice for both low frequency and high frequency application. The NCP6080 evaluation board is designed such that engineers interested in this novel topology can easily probe various signals and learn the intricacies of a totem-pole PFC. The motherboard includes multiple I/O connector and test point to simplify instrumentation and waveform capture during the evaluation process. The fast leg half bridge is implemented on adapter code here, where the fast leg switches are driven using our Onsemi NCP1680, an high voltage GaN half bridge driver up to 650 volt, while the slow leg switches are driven using the NCP51530, so high voltage silicon FET half bridge driver. The NCP6080 employs a novel current limit scheme where a simple resistor placed in the return path by ground and IC ground is utilized for current limit. So the zero current detection resistor is further utilized to drive the control of the synchronous switch in the fast leg. Additionally, the NCP6080 requires only a single auxiliary winding to sense switch node values in the positive alpha line cycle and switch node peaks in the negative alpha line cycle. These novel schemes result in the main boost switch being turned on with a minimum voltage across the switching. This is also improving efficiency and reducing BMI. Let's have a look now on some data. So here is the efficiency data. So you can see the efficiency plot measure on the demo. So here you can see that across the world load range, especially with the high line, we are quite well all above 98.5%, which peak close to 99% with the full load. While for the low line, of course, it's a little bit lower, but it's always well above 97%. Here, I would like to highlight the value at 50% load. So as you remember in the first slides, so 80 plus titanium standard levels require up to 96% of efficiency at 250 volt inputs at 50% load. So here we are quite well above, more than 2.5% higher than that specification. And this is more important. It is very important for efficiency and power consumption. Here you can see also the plot diagram for the THD. The device has a feature, another feature of the 6080 that is derived from the zero cross voltage is the THD enhancers. How it works? Simplifying, basically it produces a small on-time extension proportional to the time duration of the zero cross detection voltage and is less than a minimum threshold. Typically, at lighter load and near to the AC zero crossing, so the amplitude of the inductor current reduces and the zero cross detection voltage will spend longer duration below this minimum threshold. So this is resulting in a larger on-time extension. The THD enhancer work also in conjunction with an internal dead time compensation circuit. So this allows the NCP60 to achieve a THD which is below 10% at medium to heavy load across the universal input range. Here you can see also the power factor. So for the low line, we are very, very close to 1. I think here is not really highlighted, but we are 99 point something %. While for the low line, for the high line, sorry, we are well above 90% from the half of the load. So quite very good power factor correction. One important thing when we talk about ultra high density is also the thermal images, so the thermal scan. The NCP6080 evaluation board and other cards were also evaluated for thermal performance. So in the worst condition, while operating means at 90 volt AC and 300 watt. As you mentioned, is the worst case scenario. The thermal image of the fast leg GaN FET, so the boost inductor and the slow leg silicon FET are shown here. So this image were captured in a 25 degrees ambient environment. So with no external high flow, the high efficiency performance of the totem-pole PFC is evident here in the device temperature. So where the fast and the slow leg switches are both measured below 60 degrees. A modest, so this means a modest 35 degrees rise above the room temperature. The daughter board PCB card is also designed in a manner that eliminates the need for additional heatsink to be mounted to the board. If you remember from the picture of the board, there was no heatsink at all on the board. The PCB internal copper planes function as a heat sinking, and the temperature rise of the fast leg switches is well controlled by this copper plane. Of course, if you want to look more deeply on our NCP60 webpage, you will find the user manual, the datasheet, of course, of the board, and also some materials about tip and tricks and how to get the best performance from this device. I think I'm perfectly on time, and then we can have some times for any questions and answers.
Yes, perfect. Thank you so much, Alessandro. I really liked it. I hope the audience too. So as you already mentioned, you have now time to enter your questions in the chat or question window. So feel free to enter them. Let's check the questions. Maybe the first one. Why is wide bandgap semiconductor needed for totem-pole PFC?
That's a good question. So in which case we talk about especially CCM, continuous conduction mode totem-pole PFC being a hard switch topology. And GaN has no inherent body diode, so there is no reverse recovery charge. So that would contribute to switching losses, hence enabling ultimate PFC efficiency to be achieved. The body diode of a silicon carbide MOSFET still has a non-zero reverse recovery charge, but is much lower, for example, compared to a standard silicon MOSFET. So this expect that the efficiency of the totem-pole PFC to be a little higher with GaN compared to the silicon carbide, and of course much higher compared to the standard silicon.
Thanks a lot. Another question, I think it is related to the evaluation board. Why are you limiting the application range to 350 watts?
This is not a limit of the demo board or the device. This is a limit of the topology. So this is CRM, and this is a limited of, because if you remember how it works, so the current in the inductor moving from 0 to the peak. So this is just a limit of the CRM topology. It's not a limit of the device itself. So if you want to move to higher power, then you need to use a different control techniques, for example, multi-mode or a CCM.
Okay, thanks. And another question, why CRM is a balanced approach?
CRM is a balanced approach because, well, okay, as neither CCM or DCM present an ideal solution. So many design use a critical conduction mode, which is suitable for up to few hundred watts, as we discussed just the previous question. So CRM manage the switch frequency to operate on the border between DCM and CCM. So in response of change in line voltage and low current. This benefit from low turn-on losses, and as the peak current is limited to double of the average current, so the core and the conduction losses remain acceptable.
Great, thanks a lot. Another question, can this topology work for three-phase PFC?
No, this is not working as a, for example, an interleave PFC. This is only for single phase.
Okay. Another question to the frequency, which is the switching frequency or the range of frequency?
So the device, it comes with different options. So it's a trimming option, depends on the part numbers you choose. So in this case, we have released two versions. One is clamped up to 130 kilohertz, if I remember well. The other one is above 270. But of course, we have the possibility to go much higher, even close to 400, but not yet released.
Okay. Let me check. There's a question. How about surge voltage, EMI robustness for this totem pole PFC topology?
Sorry, can you repeat the question?
Yes, of course. How about surge voltage, EMI robustness for this totem pole PFC topology?
It's quite well compared also to the other PFC topology. So we already performed several tests on this, even on this board, and it passed quite well all the tests. But this is something we can discuss even offline for if needed more information of test.
Okay, great. I would say we will answer all the other questions afterwards via email, so don't worry, all of your questions will be answered, of course. But for now, thank you so much, Alessandro, for your interesting presentation, also for the question and answer round. And thanks to all of you for your attention. Yeah, you will get the slide of this presentation afterwards via email, and also the recording will be visible on our website shortly. A short hint from my side, at 2 p.m. there will be another Digital Day session, which is called Filter Components, Mode of Operation and Selection Criteria, from our field application engineer, Mario Möller. So thanks to all of you. Thanks, Alessandro, and
Thanks
have
a
a
lot.
nice day.
You
Bye.
too. Bye-bye.